Slavica. I would like to begin by acknowledging the Wurundjeri people of the Kulin Nations as the traditional owners of the land on which our Parkville campus stands. I also acknowledge the traditional custodians of the various land on which you are all joining us from today. I pay my respects to the elders, past, present, and emerging, and to the Aboriginal elders of other communities. So just for the people who are attending via Zoom, I just go through a quick housekeeping rules. Please stay muted throughout the presentation. And there will be a Q&A session at the end of the presentation, but feel free to put your question on the chat as you think of it during the seminar. So it's my pleasure to introduce today's speaker, Dr. Slavica Jonic. Slavica received her BSc and MSc degrees in electrical engineering from the University of Belgrade, Serbia in 1996 and 1999 respectively. She obtained her PhD degree in image processing from the Swiss Federal Institute of Technology in Lausanne, EPFL Switzerland in 2003, and a research director of habilitation from the University of Pierre and Marie Curie, UPMC, current Sorbonne University, France in 2015. She held research and teaching assistant position at the University of Belgrade and EPFL from 1996 to 2003, and a research scientist position at the UPMC 2004 to 2008. She obtained an associate scientific scientist position at the French National Center for Scientific Research, CNRS, in 2008, and a CNRS research director position in 2019. She is currently with the IMPMC-UMR 7590 laboratory, located at Sorbonne University since 2004. Her background is in signal and image processing for biomedical engineering applications. She currently leads a team working in the area of methods development for the reconstruction of structure and dynamics of biological macromolecular complexes from cryo-electron microscopy and cryo-electron tomography data. Her particular interest is in new methods for studying continuous conformational transitions of complexes, including hybrid methods, combining image analysis, molecular mechanics simulations, and deep learning. And today she is going to talk about DeepHEMNMA approach for analyzing continuous conformational heterogeneity in single particle cryo-EM images. So I will hand over to you, and please start.
Thank you. Okay, thank you very much for this nice introduction. So thank you for coming today to listen to my talk. I'm very happy to be here to speak about the work that we are doing in Paris regarding methods development for continuous conformational variability analysis of macromolecular complexes in single particle analysis that majority of you probably know already. Let's start. So as Sepide said, I'm coming from Serbia. So for those who don't know, so it's one of the states of ex-Yugoslavia. And I did my PhD here in Switzerland, and now I'm here in Paris. Avatar, I guess. But I don't know if everyone knows that Paris is divided in 20 districts, and our lab is in the 5th district of Paris, so very close to the scene. So here is our campus, and the Seine is here. And Cathedral Notre Dame, you can see from here. So we are here between these two towers. The campus is nothing like the campus is here. So it's a rectangular square. It's kind of a grid, and then you have towers and corridors between them. So our offices are somehow in this kind of buildings. And it's a kind of modern campus with a lot of artistic works everywhere around. So now, I guess you as biologists, that's evident that conformational transitions and structures are directly linked to the biological function of complexes like DNA replication, protein synthesis, or virus maturation. You have some conformational changes. So proteins change their shapes in order to accomplish these functions. So when you have like gradual conformational changes, gradual change of the shape of the structures, we speak about continuous changes of conformation. Like, for example, in the case of ribosomes, involved in protein synthesis. We have rotation between the two subunits, subunit rotation. But also you have additional motions like movement of this part here that is called L1 start. So contrary to this kind of conformational change, you have discrete variability structure, like you have binding and unbinding of substrates. So you have like two states, one with and the other without. And then you can have a combination of discrete and continuous conformational changes, like in the case of this human ATS ribosome elongation cycle. Along the cycle, the ribosome is binding different ligands and at the same time changes the shape gradually. So in single particle cryo-EM, you have a sample in the microscope that contains many copies of the same macromolecular complex in different unknown orientations. They are random and positions in a thin layer of vitreous ice. And an image is taken, like this one. This is an example with many views of this complex, like you see here top views and side views, and you need to extract these complexes into individual images, then computationally calculate their orientations and positions in order to calculate 3D reconstruction, 3D structure of the complex. So obviously we have a heterogeneity of orientations that we need to solve. So the views, different views in the big image, but also we have heterogeneity of conformations. As I said, each of these copies of the complex can be in a different state, frozen, captured in a different conformational state. So when we have these gradual changes, when you have plenty of intermediate states between some to end states, then so you have uncountable number of states, then this means a huge heterogeneity. So this is a big concern. And additionally, we have a problem with noise, because in a microscope you need to expose your sample to very low electron dose in order not to damage the sample, which actually means that the signal is very low and the noise is very high. So this is the example of particle images. So you have 4 particle images here. So you cannot distinguish due to noise if they are different orientations or different conformations of the complex. So in the case, if you have a discrete heterogeneity now of different views in the image, like in this sketch, where you have 3 different shapes, those are the kind of projections of these different shapes, then it gets, let's say, relatively easy to cluster these different shapes automatically, more or less, into 3 groups in this case, because there are 3 different shapes, so you have 3 groups. Each of these small squares is actually a different view of the same shape. Okay, so you have 3 different shapes and different views that correspond to these different views of the projections. However, this is not something that happens in reality. So we now know that the conformation changes are gradual, and so we have more or less this situation where the complex is changing gradually the shape. And if you want to represent all the different shapes in some space, we speak about low dimensional spaces like this 2D space. So you have all these different yellow squares that are different conformations. And then it's not that obvious how to split this cloud of points into number of groups and how many groups to choose. And the majority of current methods, like those that you can have in a Reliant software package or FreeAlign or other software packages, will ask you to set this number of classes before you start. you're processing. So how many classes here? You can take 3, 4. So people will run the software with different number of classes and then compare the final results and see what is common structures, common conformations between different runs. And like this retains some of the conformations. And at the end, you end up with 1, 2, or 3 different states. And you never actually can explore each of these different conformations. So in this cloud of points, cloud of conformations, actually, you have maybe some conformations that can be interesting to look more deeply into, to develop some new drugs. So they can be target conformations for drug development. So we are working on methods that are different from the majority of methods. So we are looking really to find the conformation in each single particle image and represent them in a low dimensional space like 2D or 3D that we call conformational space or conformational landscape. And our methods are based on simultaneous iterative calculation of conformational and positional parameters of each particle in each given image. For this, we represent the motion field, this conformational change, using various methods like you can use simulations. So this is the majority of our projects use simulation. That can be obtained by normal mode analysis that I represent here, or molecular dynamic simulation that perhaps you know better. And but also some other methods like those that come from computer vision, like what you see here is optical flow, but I will not enter into this method today. And then we use deep learning to speed up our analysis, because all these analysis computation are very intensive. Okay. So the point is that we first determine this kind of spaces, so like some kind of statistical analysis, and then we look and we explore the space and we decide on a number of classes that we want to reconstruct the structure from them. So we are doing it interactively or semi-automatically. We group similar conformations and then we obtain many of the states. And so you will see what we do. So this is the first method that we developed in collaboration with one group in Madrid, Carlos Sanchez Orsano and Florence Tama, who is specialist for MD simulation and normal mode analysis, and Carlos is more specialist in image processing. Florence is currently in Nagoya University, and we still have collaboration together. So we published in 2014 a method called DeepHEMNMA that uses mechanics molecular dynamic simulation by normal mode analysis to explore single particle images and to obtain this kind of spaces that then we explore. We can animate different conformational changes that we interpret from this space, or we can calculate 3D structures by 3D reconstruction from images. So I will now first present this Henna method that was the basis, and then on top of which we then build the new method that is now involving deep learning, that is speeding up the analysis. And then in the last part of the talk, I will present software that we develop and that is open source and accessible to everyone. So if you want, you can use it. And it's part of, actually it's a plugin of one package that maybe you have heard or not. It's called Scipion. So let's see all these together. So what is normal mode analysis? So it's a method for molecular dynamic simulation that actually decomposes complex motion of a system in a linear combination of independent harmonic oscillator types of motions. And each of these motions has some frequencies. So like we have low frequency motions that are the most collective motions, which means many atoms are moving together collectively synergetically, like change of the shape of the complex, but then you have higher frequencies that are more localized motions, like change of the bond angles and lengths. You can calculate normal modes for an atomic structure. So here you see two structures, atomic structures, and blue is the initial structure and red is the one that is displaced using one normal mode. So each of these arrows is showing where the atoms move, but this is one normal mode decomposed in actually many subvectors, because normal modes are vectors along which move atoms. And also you can calculate normal modes from 3D reconstruction, like those that we obtain with cryo-EM microscope. So it's density volume in gray. But in order to calculate normal modes, you need to coarse grain this kind of input, which means that we place 3D Gaussian functions. Those are here represented by spheres, but they are really Gaussian functions. And centers of these Gaussian functions then play the role of atomic centers. And then we can move them along these vectors that are normal modes. So we use Tyrion's elastic network model for calculating these normal modes as the majority of groups. Tyrion's elastic network model means that atoms, or these 3D Gaussian functions that we call pseudo-atoms, are connected with elastic springs, and this initial conformation, that is an atomic structure or EMMA, is at the energy minimum. So this is the potential energy of the system, that is the sum of pairwise energy terms, and this is one of these pairwise atomic pairwise energy terms that you see here is basically a square of the difference between the distance between two atoms, A and B, initial structure and in the display structure. So normal modes are obtained by harmonic approximation of this potential energy function. That it means that at the end, actually, what you get is that you need to solve this kind of equations that is called eigenvalue problem. Actually, you need to decompose matrix H, that is called Hessian, that is the second derivative of the potential energy function. And this decomposition of the matrix H in matrix A and L means solution of this problem. And matrix A, it turns out that it's actually a matrix that contains in the columns normal modes that are eigenvectors, and on the diagonal of the matrix L, you have frequency squares of each of these normal modes that are eigenvalues of the matrix H. Here is how you displace actually the initial atomic or pseudo-atomic structure. So those are the coordinates of this initial model. You displace it using a linear combination of normal modes A, and you apply some coefficients to scale them. So those are actually amplitudes of normal modes. So this means how much the atoms move, because this analysis is giving you the directions, the vectors along which the atoms move, but it does not tell you actually how much they move. So in order to get the amplitude of the motion, actually you need to correlate these kind of models with something. So we use the single particle EM data, EM images, to get the amplitudes. So you will see this in the next slide. So now you see that the maximum number of modes is 3n, where n is the number of atoms, because this matrix H is of the size 3n times 3n, so n is the number of atoms of pseudoatoms. So this makes a lot of modes, and the computation is very time demanding. So we need to reduce the number of modes from 3n to a smaller subset. So what we do usually is that we look at this kind of plots of what we call collectivity. So collectivity is a measure of how many atoms move together collectively, and it is scaled, it is normalized between 0 and 1. So you can put a threshold like around 0.5 and say all these modes that are above 0.5 collectivity will be the modes that I will take for my image analysis. Like this, you reduce the number of modes to a smaller set, like you can use from 1 to 10 normal modes. This is still feasible. So what we have here is an example of how HEMNA works, given single particle images and one initial model that is here and EMR. Okay, this is a reconstruction. Let's say you have some images and then you do perhaps classical classification of the images using real-line or pre-line or whatever, and then you obtain one map. Or you have some atomic structure that comes from PDB database. If you have EMR, then you need to convert it into these Gaussian functions that are pseudoatoms. Then you calculate normal modes. Here in the red, you see just one normal mode, so where these points go, the directions of the motion. Then you calculate the collectivity of each of the modes. So here you have starting from the mode 7 to, for example, 50, because higher modes usually don't take high frequency modes. Those are the frequencies, because those are very localized motions. So we focus more on global low frequency motions. And we don't take into account the first 6 modes because they are related to rigid body motions, which means translations and rotation that we solve by our image analysis in a little bit different way. So we don't need to use the first 6 modes, but just we start from mode 7. And so what we are doing is that we are taking this initial model and iteratively we elastically deform it using normal modes, and we are testing different amplitudes, and we are kind of doing fitting. If you know what is the fitting of atomic structures into EM maps, then this is very similar in the sense that we are just, we don't have a 3D target conformation, but we have 2D conformation in 2D data. And we do it for each single particle image independently of other particle images. So everything is done in parallel, it's parallel processing of images. And at the end, we get for each single particle image 3 other angles that determine the orientation, 2 shifts in plane, and conformational parameters that in our case are amplitudes of normal modes. So these Qs here are determining our conformations. So we have a set of Qs for each of the single particle image. And let's say I say here we have M normal modes because we selected from a number of modes. We selected a small number, like here, for example, we used 6 modes to analyze these images. So our conformational parameters are amplitudes of normal modes, because if you apply these amplitudes for a given set of vectors, normal modes, then you know where these atoms go. So this determines you new conformation. So at the end, we project, we represent the Qs that we obtain for each particle image into some low dimensional space by doing PCA, principal component analysis on the Qs. So each of these points, blue points here, is one single particle image, and close points correspond to similar conformations. And those that are far away correspond to different conformations. So obviously you can group similar conformations you can group similar close conformations into 3D reconstructions and then calculate new conformations. Or you can, let's say, displace this initial model along different directions in this space and animate the trajectories. What we call trajectories are kind of, we fit we do least squares feet of the data points in this space to get the trajectories. Or you can also manually draw these trajectories. So this method, Henna, was applied on different structures, on different shapes, I mean, architectures and sizes. That was the first one, the DNA polymerase pol alpha B subunit complex with negative stain images that were previously analyzed by the authors here in using maximal likelihood, 3D maximal likelihood method that currently we have in Relier. And they obtained three formations with different degrees of deflection of the flexible linker between the two rigid lobes. So we took one of these conformations and then we reanalyzed the same set of images. So we could get this conformational analysis more extensively done, which means that not only we observed this flexion between, I mean, opening, let's say opening and closing or between the two lobes, but we also could observe the extension of the flexible linker. And yes, I had a movie here that does not start automatically. So this is one of these lines, let's say the line in the middle that we animate using, let's say, the initial structures, initial model. We displace along this red line, and you get this kind of combined motion where you have opening and closing between the two lobes, and then you also have the extension of the linker. This is another example on a virus, tomato brush stunt virus, cryo-EM images. So we took the model of a compact form of the virus because in the native form the virus is fully symmetrical with 60, I mean, icosahedral symmetry on the capsid. So we placed Gaussian functions that you see here overlap small spheres, overlap on the 3D map reconstruction. And we calculate normal modes. So as you can see in this case, for example, all normal modes are highly collective because of the symmetry, because it's a big virus. So instead of putting the threshold on the collectivity to 0.5, we increase the threshold to 0.75. Because if we kept the threshold 0.5, we would take all modes. This is too much for analysis of images. So we selected only 4 modes and we analyzed cryo-EM images, and we obtained this kind of conformational space that we split then in 4 groups, and we calculated the reconstruction. So you can see the swelling of the virus. So the capsid is changing the radius, and this is due to the actually change of the pH pH of the solution in which the virus was, and this is the conformational change actually along this line in the middle of the cloud. Of course, I mean, this is exactly what I'm saying. So it's called swelling of the virus. It looks very symmetrical motion, but of course there were some other motions that were asymmetrical, for example, but they are not presented here in this video. So this is another example where you see Escherichia coli 70S ribosome with and without elongation factor G. So we had a number of cryo-EM images in which we had a mixture with or without EFG, and we had to kind of split between the two groups using one initial model. It was again an EMAP. So we represented it with Gaussian functions, and then we selected the mode that describes the rotation between the two subunits. Okay, so this is the motion that is known for ribosomes. It's called ratcheting motion, where the two subunits rotate between each other. So we just took one normal mode and analyzed the images, and we obtained this kind of conformational space, but it is just one-dimensional space. Actually, it is called histogram. So here on the x-axis, you see the amplitude of the normal modes for each of these images. Actually, this corresponds actually to the rotation of the value of the rotation, the amount of the rotation between the two subunits. Here you see, for example, how many images had this rotation, how many images had that rotation, and etc. So you see that there is kind of a distribution, continuous distribution of the rotation between the two subunits. And still, you can try to combine the images at the left and the images at the right in 3D reconstructions. So this gives you two volumes, two 3D reconstructions, where you can see first this rotation between the two subunits. You see gray and yellow are actually two conformations, and there is inter-subunit rotation between them. And also, you have in one of the two, we could observe this EFG factor bound. In another one, we didn't see. Also, you can see tRNAs bound. And even if we just took the mode that describes the rotation between the two subunits, we could also observe the shift of L1 star. So this is a case where you have actually a combination of continuous and discrete discrete heterogeneity, because continuous means this rotation between the two subunits, gradual with many intermediate states, and this continuous, and discrete means you have this binding and unbinding of EFG factor. So our approach does not use classification, at least not before we get this conformational space. In the conformational space, we can look and see how many clusters, classes, or groups we want to extract, and then eventually calculate 3D reconstructions, or we don't need to reconstruct at all. We can model the transition by displacing the initial model along some trajectories. So this is interpolation actually of the conformational space. And another message is that when you have you suspect, for example, discrete heterogeneity, so you in principle need to use traditional methods that are based on classification, like relying on realign, to kind of pre-classify your data, and then use this method to more extensively analyze gradual changes around these different structures that you obtain with realign or realign. Now, in case of ribosomes, this is not necessary, because actually the rotation between the two subunits is enough to because it's correlated with binding and unbinding of some factors, and usually you can get the conformational variability analyzed without previously using these classical classification-based techniques. So everything is good with this method, but it's first of all very time consuming. And secondly, yes, how we select these normal modes. This is not always obvious. For some shapes, I mean, we have some guess how to select. We can also look at the collectivity, but yeah, this is a little issue. But with some training, you get to know how to select the normal modes. But from another side, the time is very precious, and even if we are doing the calculation on parallel computers, maybe in parallel on many images, it's time consuming. So we decided to use deep learning to speed up the analysis. So what is deep learning? Actually, we are using supervised learning. So in classical classification algorithms, you have, for example, a number of inputs, and you label them manually. Say, okay, this is dark, this is not dark, and then you train the network to learn what is dark, what is not dark. So here you have two classes, and at the end, when it learned, it is able to predict if this is dark or not for a new input that was not seen during the training. So you have a training phase and you have a test phase or prediction phase or inference phase. I mean, there are different terminologies here. In our work, we don't do classification, so we don't have a number of classes. You could imagine to do this, but our idea was to use this in the regression learning, which means to learn values of each of the parameters that I mentioned before, which means 3 Euler angles, 2 shifts, and m parameters of the conformation. So we really learn their exact values, okay? So still in the same fashion. So you have a number of inputs that are our images and a number of outputs that are for each image 5 rigid body parameters plus m elastic parameters. And the learning of the relationships between the two is done through a number of hidden layers of neural network. So in one hidden layer, you have nodes, neurons that are connected with some of the nodes from the previous layer. And like this, the network learns complex nonlinear relationships between the inputs and the outputs. And so in our approach that we call DeepHEMNMA, we use in the first step classical, I mean, no, just the approach I explained before, HEMNA, that runs on a small subset of images, like 20,000 to 40,000 images should be enough to train a network to learn the relationship between single particle images and, we run HEMNA to get on 20,000 to 40,000 images their orientations, their centers of the particles, I mean translational parameters, and conformational parameters, these and normal mode amplitudes. And then the network is trained using this set of images and the corresponding rigid body and elastic parameters. So the network will learn the relationships between these inputs and outputs, and then will be able to predict this rigid body and elastic parameters for new images. So the idea is to use for the inference step, for this test step, once the network is trained, a larger set of data, like 1 million, 2 millions of images. While here, for the training, you train on a very small set on which you can run HEMNA, because this is still feasible. So you will see some numbers, I mean, how much we gain in speed very soon. So in our work, our DeepHEMNMA uses a very deep neural network. The neural network has 34 hidden layers, and it's of the type of convolutional neural network. So I will not enter into all these technical details, but basically, okay, what we are doing is that to learn the relationship between the inputs and outputs, we are minimizing some error between, and the error is mean absolute error between the given outputs and the predicted outputs. So this is why it is called supervised learning, because we give the example and the examples, and we want the network to predict the outputs with a minimum error with respect to the given examples. So we can either train 3 different networks, because we have 3 parameters, orientations, shifts, and conformational parameters, or we can have one single network and train it to learn all of the parameters. So of course, if you have single network, then it will be a little bit faster. But if you train using 3 different networks, then you can use different numbers of images for the training or different parameters. Because in some cases, you need more images. For example, typically we observe that for learning orientations, we need more images than for learning conformational parameters. So, okay, one or the other have advantages or disadvantages. So that was tested using first synthetic data. So we synthesized data from adenylytic kinase. That is a typical structure that modeling people are using for testing their methods. We applied noise, the signal to noise ratio of 0.1, and the focus. So we simulated microscopy conditions, 0.5 micrometers, and we randomized the orientations and shifts, and also the amplitudes of motions along 3 neural modes. So we use 3 neural modes to simulate some conformational dynamics. And we decided to use this kind of relationships between different amplitudes of modes. So you see some sine and cosine relationships between them. That is totally artificial, but it helps us to actually visually see quickly on this kind of curves that are, first of all, nonlinear, but also look easy to inspect if our training and prediction went well. So this kind of relationships between 3 amplitudes give us this kind of parabolic shape curve. So in black, you see what is ground truth, which means this is the true value of the normal amplitude, those that we synthesized. And then in blue, you see what Henna estimates, and in red, you see what neural network predicts. So you can see that neural network predicted quite well with respect to Henna. They are very similar, like in the outputs. And all this was done on downscaled images. We synthesized this size of images, and then we downscaled to 128 in order to get faster processing. And the training was done only using 14,000 images, single particle images. And prediction, what you see here is, you see the results for 2,000 images, okay? And in machine learning terminology, you have this kind of names like training set, validation set, and prediction set. So training is the set on which you train the network. Validation is something that you test the network if everything is good during the training. But then prediction is really what you give to the network once it is trained. And each of these 3 sets are totally different images from the same distribution. So this is visually, you visually see that neural network predicts quite well. Almost it gives you the results as Henna, okay? And then numerically, quantitatively, you can quantitatively evaluate your error, the amplitude error prediction with respect to ground truth is 7.5. Okay, that is, let's say you have to put the 7.5 relative to the range that we had in amplitudes. So it is between -200 and 200. So these numbers I didn't say, so they don't have physical units here because the physical units are on the normal sides. For normals, we give angstroms, but these amplitudes just don't have physical units. So anyway, 7.5 with respect to 400 is quite little error. And then we also can see this error in terms of root mean square deviation. So which means you apply the amplitudes of modes, I mean, the ground truth amplitudes on the structure and the predicted amplitudes on the structure, and then you compare the two structures, I mean, mainly because you have many images, and the average root mean square deviation between these structures is 0.4 angstroms. Okay, so this is small. And with this, we could test also how this network also predicts angles and shifts. Okay, because what I just explained is how it predicts normal mode amplitudes. What we saw just before is the average for 3 normal modes, but then you can see for each of the normal modes how it behaved. But then you can also see how it predicts the angles. So this is the average for 3 angles, and how it predicts the shifts. So obviously it has the most difficult to predict, to train, to learn actually the angles. It's quite reasonable error, 2.5 angstroms. This is the mean. Standard deviation is 3. And then you can see what this means in terms of root mean square deviation, because as I said, before we just saw that for normal modes it's 0.4, the root mean square deviation between predicted and ground truth values, and for the angles you see that the mean is 0.9. So it is bigger, twice bigger than for normal modes, but it is below 1 angstrom. Okay, so it looks reasonable, and shifts were predicted quite well. This is actually now the same train network applied on 50,000 images, synthetic images, and splitting the space in 10 groups and reconstructing different conformations along these distributional points. You remember each of the points is actually one single particle image, for which we have, of course, 3 other angles, 2 shifts, and conformational parameters. So we can gather them together, group them into 3D reconstructions, and you see, for example, different resolutions that we obtained for different structures reconstructed. And you see how many images we used for the reconstructions, and you see the overlap between the reconstruction and the atomic model that is actually the centroid of each of these groups. And the resolution was calculated based on the Fourier correlation between the reconstruction and the simulated map from the atomic structure with a threshold of 0.5 on the Fourier correlation. So in terms of processing time, I mean speed, for this case of using 3 normal modes and this data case of synthetic data, we speeded up Henna by more than 40 times. What does it mean? So here is, for example, the architectures on which we did the calculations. So Henna, for 20,000 images on 160 CPU cores on this CPU frequency, 2.6 gigahertz, takes around 8 hours for the size of 128 square pixels. training of the network using 4 NVIDIA V100 GPU cards with around 5,000 CUDA cores. Training with 14,000 images takes 20 hours. And then the prediction using just one NVIDIA card of this the same type is like for 50,000 images, it's 5 minutes on small images. But if we want to predict on 1 million images, then it is less than 2 hours. While, for example, HEMNA, if we want to run HEMNA on 1 million images, then we need 400 hours times 160. Okay, so this makes like 44 times faster processing. So all this is done on our supercomputer, Janze, that has a GPU and CPU processors. So also all this work has been published actually relatively recently, maybe in August. And in the paper that was published, we also presented the results with experimental data that are publicly available under this code in NPR database. Basically, it's yeast, ATS, ribosome complexes with tRNAs bound. The processing of original work was done on 90,000 particle images by the authors of the data using free-align classical classification in 5 classes. From this, they selected 2 classes with around 20,000 images each class and obtained 3 reconstructions, each around 6 atom resolution. One of the reconstructions is a reference structure with 2 tRNAs. So here you have this representation, 2 tRNAs in classical EE and PP position. And the other one is a conformation with inter-subunit rotation with respect to this reference of around 9 degrees with 1 tRNA in hybrid PE position. And they also derived 2 atomic models and deposited them in the PDB. So we started from this data set, and we took actually 2 groups of images with in total 46,000 images. We have so mixture of 2 classes with 1 and 2 tRNA. Then we downscale the images from 360 square pixels to 128 square pixels, which means that we have the pixel size of 3 angstroms, more or less. And we split the data set in 3 subsets: training set of 32,000 images, validation set of 2,000 images, and prediction set, inference set of 12,000 images. This gave us this kind of conformational space in two-dimensional conformational space by principal component analysis that we then split along the principal axis 1 that shows the most variability into 7 groups, more or less uniformly, so that we get at least 900 images in each of the groups. So from each of the groups, we reconstructed an EM map. You see here below the number of particles used for each of the maps, and you can see different degrees of the inter-subunit rotation between the EM maps. Actually, this rotation is mostly visible here, and you here see actually also different states of presence or absence of the second tRNA. Then we can also take more images at the left and reconstruct one EM map, and more images at the right reconstruct another EM map. This was done, and superposed with EM maps of real line. And we could see again very similar rotation with ratcheting motion of the ribosome, and also we could observe in one map one tRNA and another two tRNAs. But yeah, but obviously, I mean, the advantage of this method is that you can get with a much smaller number of images, actually, you have a better view of the conformational heterogeneity of your data set and get these reconstructions, although maybe at lower resolution, but with much smaller number of images, because actually we are analyzing really these images individually. We are not classically, we are not aligning the images between each other. We're just aligning each image with respect to an initial model. So this actually allows you to go up until the very end, totally, I would say, independently and individually. And so, okay, so she's coming. So I guess it's done. Yeah, just to show you quickly. And so all these methods are available in Continuous Flex. This is a plugin of Scipion. And not only methods for analyzing single particle images, but also the methods for continuous conformational variability of complexes in subtomogram data, which means that you can analyze conformational variability from in situ tomography data. And so this is another technique. So I don't know if you know or not, but we have also some methods how to deal with missing wedge. For those who know, so it's a little issue with tomography, because you need to tilt, and then you cannot tilt. You cannot have a full tilt range, but you have to stop at around 60 degrees. And so we have various actually methods to deal with both single particle images and subtomograms. And for this, we can use normal mode analysis, but we can use also image simulation and optical flow and with deep learning, and you can get the conformational analysis in situ or in vitro. And yes, I should okay, I will go directly, because okay, all this work, especially putting all these methods together, I mean, software was done thanks to Mohammad Harastani, who did already first work, because initially Henna was part of Scipion and we extracted it from Scipion, and now we are trying to maintain it as an independent plugin in which we put all our methods. And Remy, who is with you for some time more now, he is a joint PhD student between Sorbonne University and the University of Melbourne, who does great work on combining classical IMD simulation with actually subtomogram analysis and also single particle images. And this is also a work that we currently have under review, how you can now, instead of normal modes, use ND simulation to analyze 2D data, which is quite challenging, but he did a very good work on this. And the software is also allowing you to synthesize data. For example, we can synthesize images or synthesize subtomograms or synthesize EM maps to test different methods in Scipion. And we also provide the data that we synthesize on Zenodo. The data can be synthesized with conformational variability or without, with also different distributions of angles and shifts. And so, okay, so once again, I should thank my PhD students, Mohammad Harastani, who actually just finished, and he is now a postdoc, Iris Hamitush, who worked a lot on this method of deep learning, Remy, yes, normalized MD, master student Nima Barati, and postdoc Alex Mirzi. And then I have, of course, many collaborators to thank to. Also, Jose Maria Carasso lab in Madrid. I mentioned Carasso Social, but there are many people there who helped us, like Jose Miguel de la Rosa Trevin, Floros Tam Lab, Isabel Ruia Lab, and then Ribosome, current collaboration that we have with the Bruno Clouds. And then nucleosome data that I couldn't go into, those are the data in situ, with Michael Edson and Amelie Le Forestier, and we have currently a small collaboration with the lab of Martin Beck for the subtomal analysis of SARS-CoV-2 spikes. And thanks to you for your attention, and I'm open for your questions.
Thank you for a great talk. I think we are running out of time, but I think you can always stay for a little bit longer for the questions. So anyone, if you have any questions?
Yes.
Yeah.
We need Mike, or we're just going to go out?
You just can.
Great talk. Thank you very much. I guess I got a few major questions. It seems like Henna is redoing calculations that have already been done. So it's recalculating all the Euler angles and offsets.
Yes.
Why not take them from whatever software package that has already seen these particles?
Okay.
Because then that will get rid of the first six normal modes, right?
I don't know. We never. I mean, I never thought about this. I really wanted something to go from scratch.
Okay.
In some newer methods, we are trying to use some orientations obtained by some other software. But let's say I had a philosophical problem with this approach, where you take the orientation from somewhere else. I mean, because at least when we started all this, 10 years ago, it was not that obvious. I mean, what all these kind of classical classification methods are giving us, because normally when you know that there is so huge heterogeneity, okay, if heterogeneity is little, that's fine, then you get probably these orientations relatively good, well, using this classical classification method. But if the heterogeneity is huge, and then you do classical classification, then you have a good chance not to get these orientations correctly, because you have a combination of continuous heterogeneity and angles, and they just try to do, at least 10 years ago, in very small groups, very small number of problems, like 2, 3, which means that you're obviously wrong.
No, I get that. You're still getting that. You're still taking particles from some form of consensus refinement on your data that has produced a map at some level.
Yeah.
So I guess at this moment, it doesn't matter if you're using pseudo-atomic model anyway for deformation and normal mode analysis. It doesn't matter then, right? If you've already got pre-calculated Euler angles from this, it seems like there's an extra couple of computation steps that you can cut out.
Okay. I mean, you can probably start with it, but the software currently is really doing like in 2 steps, a kind of in each iteration have rigid body alignment and then followed by this kind of canonical alignment. And this rigid body alignment starts with exhaustive search of particles. So actually, you can adapt, it is not implemented like this. It is implemented to really first look everywhere, as if there is no option currently in the software to start from some angles. But yeah, maybe this could be added as an option to start from some initial angles. But okay, it's the implementation is not that simple, like to add this option.
Can I ask one more? Yeah. So I guess with the pseudo atom whether you start from a PDB or a Gaussian approximation, also seems to be extremely computationally intensive. Because let's just say with Ribosome, that matrix that you end up with is humongous, right? And that's can be very computationally intensive, even on really good GPUs. If you've already got a PDB, it feels like there's many assumptions that you could make to simplify your pseudo-atomic model. For example, like RNA helices aren't really, you could define them as like a cylinder, or an alpha helix in a protein you could define as a cylinder. And then you could have like, you could really de-dimensionalize your matrix a lot.
Yeah.
Have you thought about these approaches?
Yeah, I did not mention, but of course we have considered either to use just cross-grain model, which means just carbon alpha, a model of the atomic structure, and
That still could be lots and lots of atoms, right?
And also, you know, the matrix that I showed there as exclusion, and this is like standard way of presenting how we calculate on this. But actually, when we have atomic structure, then what we have actually another approach where you decompose the atomic structure into blocks that are rigid blocks. They can just move in rotation and translation. And so like this, you can reduce a lot actually the computational part or time, because if you can split the structure into very few blocks, and then you reduce the number of atoms, you reduce the number of atoms, the size of the, for example, fashion matrix. This is what you are speaking about with the normal analysis. Normal analysis part can be, you know, this calculation what can be fast. Actually, the problem here is not really at the side of normal calculation, but at the side of using the normal to analyze it, because you have many images, and then you do doing analysis and you know. I don't know if that is what you
I'll want to chat to you more about this,
Yeah.
actually.
Okay. I see that you're the expert. A little bit not.
Which is very interesting.
Okay, but
Any more questions?
Yes, quick one, just a curiosity, could you potentially train your network on views, like a subset of views of a protein? And do you know how well it would do if you gave it a different view that it hasn't seen?
about this, what we are doing in this, I don't understand maybe the question, but we give actually
But
randomly, you know, random distribution of images, so there you have many different views.
yeah, I don't mean like different particles that I haven't seen, but actually different views, so like a completely different angle
But
of
this
the
is
protein.
what I'm saying.
You do, oh, you do that.
Yeah, of course, we put totally different angles, because, you know, it's random distribution with random angles. So when we train with random angles, and then once the method is trained, of course, we put some image with any angle, so it should predict the angles, whatever is the orientation of the platform side.
So, yeah, so maybe we can talk later.
Yeah.
Yeah, I think you can continue the discussion over the equation. Yeah. I would like to thank you all who joined us today. First, we just thank the speakers who gave a great talk.
Thank you.
Yes.